Test. Test. Okay. I guess it's a small room so everyone can hear me. Hi everyone. Today I'll be talking about modularity in software-hardware interactions for experimental physics and just generally presenting an example about it. And I know it's kind of like experimental physics is kind of a unicorn here, but I think it's something that we need to talk about. So just to get a feel of the room, who here has worked in experimental physics before? Okay, we have 1, 2, 3. And who here has written code to run their experiments? Oh, quite a number. Yeah, so actually, the truth is we all tend to, at some point, write code for our, to run our experiments in experimental physics for various reasons, right? And this is a code that we see very often, unfortunately, right? So what we have here is code that actually I have written, and I find really frustrating looking back at it a few weeks later, and I just realized the way I wrote it is just really unclear. There's barely any documentation. Everything is kind of together. There's not really that much separation. It's a bit messy. It's written hastily. It's written for one-time use, and it was not great. But the question is, can we do better than this? Well, if I'm here, the answer is obviously yes. So take a look at this. This is much shorter, right? It's much cleaner. And what if we want to do more? We can also do more, right? And this code itself actually is clean, is readable, and is short. And this is something that I would like to push for today. So the truth is, software-hardware interaction is often essential in experimental physics simply because of the complexity of the experiments. I'll stand to this side, hopefully there's less echo. So the truth is software-hardware interaction is often essential in experimental physics because of the complexity of the experiment, the analysis, or because of the monotonicity of like characterization tasks and things like that we have to do in experimental physics in order to back up our data. And so what this results in for many scientists in experimental physics is that you either do the manual labor, or if you say, okay, you know what, this is not happening, we're going to automate it, you write something that it's only used one time, it works for me, that's great. And for those cases where you have to look back at the code and like in a couple of weeks and then you just look at it and you just struggle. So that's usually the 3 outcomes that we see within experimental physics. So what does that concretely mean for us, right? So the problem we have in experimental physics is that equipment gets often left over from back in the olden days. And like, who still remembers ActiveX? You know, that was from, we have 1 person, yeah. So that was from really way back, I think the early 2000s. And like, I wish Microsoft had gave us like a memo on it because that was such a nightmare to work with like modern programming languages. Yeah, so one problem we have is just very old equipment. And on top of that, differing standards across the industry over time with different equipment working together. That's also another problem. And the last, and I think the most important problem that we have is that the results tend to be valued more than the quality and the longevity of the code. So that's something that I guess we need more convincing of like the group leaders and things like that. But that is something that I think is, I guess in this case, not super unique to experimental physics, just unique to research in general. So what is the aim here? We want to speed everything up, and we want to be able to import and use the code and just make things happen, right? And I would argue that having modularity actually helps us in that. And so I'll present the example that I created, which is called nanosquared, and then it is like an open source measurement automation kind of package in Python. And the thing is, I'll just talk a bit about how I did it and just act as an example. So what is the context of this project? So what we had to do in our laser lab was to make repeated measurements of this laser beam quality factor called m squared. And this, until now, has been done manually by scientists, by postdocs, by PhD students or master students. And there's a lack of readily available interfaces with general lab equipment. And the fact that we are working with a special wavelength of light meant that we couldn't just buy something off the shelf and use them. And so what we had was a lot of manual labor, quite a bit of delayed feedback, because imagine we do the measurement and we do the analysis by ourselves, and it is not scalable, right? If we had to do it 50 times, that's someone's like week just gone, which is totally inefficient. And so what I created was this project called Nano Squared, and the way I kind of partitioned it was to just have really like clear separation of different modules and different packages. And so on one hand, we have the pure software classes, which is basically in terms of fitting the data that we've gotten, like kind of like a quick analysis. And on the other hand, we have the hardware interfacing classes, in this case, the beam profiler and the stage controller. And so the beam profiler only talks to the beam profiler, and the stage controller only talks to the stages. And so how does that look in concrete? So let's look at the code structure. So we basically have, for every single type, an abstract class. And so for example, for the beam profiler, we have a camera abstract class, which just says all the methods that a camera class should have. And then, so this kind of became like a playground to really look at how we can do software and hardware interaction within experimental physics and just kind of like do as best as we could, right? So there is a lot of separation here. And so in this case, the good thing is, so the blue arrows there means that the A is a dependency of B, and the yellow arrow means that the A is the implementation of B. And so in this case, it is made infinitely extensible in the sense that if, let's say, a new beam profiler comes onto the market, we just need to write the interfacing code for it, for whatever vendor, whatever method, right? And we can just plug it in, and the code will work exactly as it is. And we do the same for the controller. And for that, we actually have like quite a bit of configuration classes because of how the different stages work. And then we have the fitter that does the thing. And of course, another very important thing in experimental physics is that we want to know what is exactly happening, and we want to actually keep track of what is happening. And then so in this case, what I also did was to have a logger interface to just be in every single implementation to say, like to act as a standardized way of making sure that everything is documented, every single measurement along the way. And so what is the result of that? So the result of that is this piece of code that is really very clear and very easily customizable and extensible. So on the top there, we have individually importable modules. There's clear separation. Every single module is reusable and extensible indefinitely to a good extent. And it is very good for component-based testing, which means that I can test every single component talking between the hardware and the software and make it such that everything works properly. On top of that, we can leverage on Python's ability to have auto-opening and closing of hardware interfaces with statements. And that's something that generally, when it comes to interaction with hardware, something very important. Because if you don't properly close something, maybe you wouldn't be able to do it, to run the code again unless you restart the computer. And so something like that is very good in Python that we can leverage on. And thirdly, it is configurable, but it is entirely abstracted, right? So every single knob that you have, it's documented and it's available for use. And that means that we really abstract away most of the disgusting stuff that we need to do in order to communicate with hardware and just make it such that scientists can do their work quickly. And so what are the benefits here? So if we look at a fair principle, the interoperability of old code with new code is made far simpler. And then the code itself has become more reusable. And because of the API, now the code is more, there's a bit more longevity to the code, which means that we don't have to rewrite the code every year because something went wrong. And also, it accelerates a lot of development software-wise and research-wise. Right? It automatically also provides structure and helps with documentation. So it's not perfect, obviously, but for most cases, it is good enough. So for some people who know about experimental physics and know about like hardware-software interaction might ask, what about VISA? Right? It is a standard that's been created almost specifically for this purpose. So yes, it's great, right? It speeds up development. But on the other hand, we have IDs without meaning. We have limited device and vendor support. In fact, the devices that I worked with, not all of them supported VISA, and which means that we had to actually find different ways in order to talk to them. And the commands themselves are not obvious unless you look up like really a lookup table of commands and just check out what the options are. So it's actually great if you wrap it up in object-oriented code, but it is not great by itself. So this is kind of like a solution to improve a standard that we have. And so the outlook is that the code in experimental physics has been getting better versus 10 years ago, with more people with more software background coming into experimental physics, but not enough people value good code in experimental physics. So what I'm trying to bring across here is to tell people, let's do it. Let's advocate for better code in experimental physics. Talk to your experimental physics colleagues, or if somehow this topic comes up, to just talk about how reusable code, like how good it is and why it's good, and just if you work in experimental physics, then write reusable code with modularity from the start, because if you start from the beginning, then it's not as difficult than if you have to refactor the entire code. And time invested is pain saved in the future. So modular software is not difficult, and do it from the start. And so in the end, I would like to acknowledge my team here at LMU and MPQ, and also my mentor, Annalena Lamprecht there, for giving her advice and comments on my presentation. And thank you, deRSE, for hosting, and thank you for your attention, and write good code. Yes, I see a question there.
Yeah, so thanks. It was a really nice talk. But like when it comes to experimental physics and software, you a bit mentioned, but there is this elephant in the room called LabVIEW. And
Yes.
So like, I mean, it's very bad. And it is there. There is no possibility of interoperability. There is no community. There is nothing. And most of the things that experimental physicists are just stuck there. And because it is very easy to operate in the start, but then it is impossible to do anything sustainable there. So this is the first question that it's not a question actually, I just direct, but like, do you have any kind of more, let's say, soft skills to counter this? And the second is related to metadata, like, but I can.
Yeah, okay, so I guess I'll answer your first question about LabVIEW. There is indeed a thing. I have worked with LabVIEW. The thing is, it's not so terrible if you look at it from a computer science point of view, to say that this is a different way of looking at code, to say this is data flow programming, to say how do we handle the data flowing from one part to another. It can be made operable in the sense that you make like VIs that kind of like do one specific thing, but it's not great. It's very difficult to do version control. It is very difficult to track changes in general. But yes, I do agree with you that to get started is much faster. So I think the issue here is that we need to invest time in infrastructure, because this is infrastructure, right? If we create for every single equipment that comes into the lab, to say that we write a quick interfacing like class for it, to say that if we want to automate it in the future, we use this class, then it's investment at the start that then pays off in the next 5 years when we run the experiment. Because experiments don't get built up that quickly, right? There's a lot of things that come in, and if we do the investment at the start, it could really save us a lot of trouble at the back. And we don't have to resort to LabVIEW for that, right? But yeah, I do get where you're coming from. Yeah.
The second question,
I guess we could go to our second question. Yeah.
about the metadata, because most of the time that these instruments produce extremely a lot of metadata, like for example, if you have a manipulator, like you can collect angle and stuff. But how you deal with this in that context? Do you collect this, I don't know, positional power meter or this type of things, and how you do you have other classes than the standard ones?
So the way I did it for this one, because at that point in time, it's also a consideration, right? Because there's a lot of like configuration data outside of what that's necessary here, like just generally like what's the condition of the environment, right? If we run the same test on different days, the humidity might be different and we get different results, right? And so for that, what I did for this one was to just have like, I actually made kind of like a CL command line app on top of everything. And then in this command line app, there's a part where you just say, okay, is there any metadata you want to include? And in the case of code, what I did was to say, okay, there is a metadata keyword that you can put in, and that is just kind of like a dictionary of like key values to say, okay, yeah, the humidity is like 83% on the day of the experiment, things like that you can put in. And that can also obviously come from equipment itself to go into the metadata, because I guess it depends on what you want to use it for, right? If you want to use it simply for documentation purposes, then it just has to be there, and it gets into like the data file output, and then that's it. But if, let's say, ultimately you need it for the calculation, then that's something that you need to then extract from the equipment itself. And the thing is, if, let's say, you really implement a method to extract all this data, let's say the temperature or whatever, then it makes it easily accessible. It doesn't need to be accessed, but the fact that you make it available means that it just saves you time and pain. But yeah, I do agree with you. Metadata is important. Yes?
How are you testing your hardware classes or the connection between hardware and the software?
So in testing in the sense of like testing whether it works in the development phase, or like?
I leave that to you.
Well, most of the testing I did was with the software, the hardware itself. Like the part where like you could actually separate it out into different parts. You could just test the camera itself or test the controller itself, and that just doesn't need to be in the lab, right? That can be connected to your laptop in the office where you can do the testing rapid fire. And then you do see like some problems don't come up until you actually test it in the lab itself. But of course, then that then becomes expensive testing, right? Because in the office, your testing is fast. You can just do it multiple times, and you can even run. I also created this thing called development mode, which kind of just emulates all the cores so that you can separate the software from the interfacing part of the code. But when it actually came down to testing with the hardware and everything together, it was, I would say, really expensive lab time, because it means that I had to, like in our case, was just working with lasers. And at that point in time, we only had one laser, which was going to be rebuilt multiple times, which is also why we needed this scalability. At that point in time, there was one laser, and if I wanted to work on it just to test my software, I needed to block that laser, which means that the other scientists, like the postdocs, the PhDs, could not work on it. And that's, I think, not a great part about software-hardware interaction. That is great if you have it at the beginning, because then that means that afterwards you don't have to do that kind of testing, where time is perhaps more valuable than at the start when you're developing things. Yeah. But if you're talking about accuracy in terms of software testing, like unit tests, things like that, I must admit, I only had very limited testing on this one, simply because there wasn't that much development time, and the fact that the testing was kind of like very conditional on me having the hardware. And that means that there isn't really an opportunity to do automated testing like you would have with pure software like classes, that you could just say, you know, I would like to do a few tests, run it, 2 minutes, I don't know, it's done. Then I can know, yes, yeah. Or do you have suggestions on how to do it?
Look into mocking. It's quite amusing how many problems you find even though you mock things out. So you can mock calls to your hardware maybe.
Yeah, I think it's also, I mean, I do a bit of like mocking, but it's not 100% mocking. It's just really just, okay, I expect this data to come out from my device, and so I kind of send that back, right? But that is a very limited test case, I think. So ultimately, whether, because interestingly, I can show you something that only came out after I did the thing, was, sorry, I have a lot of backup slides. So this one, what happened was that you kind of expect the data to come out really consistently, right? But what happened when I actually came to test, like, because the laser that we had was pulsed, and so you actually had variation every time a single pulse went through the system. And then so this is the beam diameter measurement that I took, and you could see that for this run, there were huge variations. But for this run, you had a huge variation at the front, and it kind of just like kind of plateaus out and everything is fine, right? But so these are things that you don't notice when you're testing like without the hardware, or like just testing within a very controlled environment, because this I can emulate very easy. This, I don't know what's the underlying like problem there, like what is causing this. I have no clue. And we actually spent about a week on this, looking into it and like seeing what is happening there. And we didn't know. We didn't know. We contacted the vendor, and then they basically said, well, it shouldn't happen. so we were also really perplexed and like we didn't know what to do. And then so ultimately it came to a point where we just, okay, you know what? We just decide kind of like heuristically to say we're just going to ignore like when there's huge variations. We just say we take until that there is some stability in the result. But of course, you know, that's not super great when it comes to like how long the measurement takes, but yeah.
Yes, we still have time for more questions. Which programming language are usually used for contacting with the hardware?
So usually what happens is that when experimental physicists write code, it's usually in Python or LabVIEW. And then the communication itself is usually done either via serial, like serial communication, like baud rate, things like that, and you kind of just set everything up. Serial, like SEIAL, right? Serial connection. Or that's usually done over like the RS232 port, if you're familiar with that. Otherwise, if it's USB, then they tend to have like some protocol on top of it that is from the vendor. Like the vendor would make some, I think they call it SCSI, something like that. That is like a command palette that you kind of send down the chain, and then it kind of gets interpreted into like USB packets, and then that kind of does that. So the thing is, a lot of these like communication with hardware, like on the hardware level, like what bits and bytes to send down the stream, has already been done either from the vendor side or from some hardworking individual 10 years ago who when the equipment first came out. And then so that kind of just is abstracted away, and it's independent of the language that you use on top of it.
Do you also have bridges between Python and programming language C?
So I personally didn't do that, but it is possible. I tried it to not so much success. And then so what happened was that, like this part, right? Like they made an ActiveX, the vendor themselves made an ActiveX pipeline, I would say, like a COM object so that code could talk to it. And at that point it made sense because it was like the standard in the industry when they first developed it, and that was like 20 years ago. Yeah, approximately there. But the problem is now, like even with Python, with like PyWin32, it didn't work very well. And then so what ended up happening after actually talking to like the head software developer there at the company was to actually use C# as kind of like a bridge. And then so we kind of use C# to make a DLL that talks to the COM. It kind of just marshals all the commands from the Python. So you can imagine this was a terrible thing to do, right? And I spent like, I don't know how, like I think a good month of development on this, simply because like I had to arrange a meeting with the vendor and things like that. And so this basically talks to this just like by calling .NET, like Python.NET methods. And then this one then just says, okay, I would like to use the COM interface, and then just sends all the parameters down the chain. And then once it comes back, wraps it back up in something that Python understands, and then send it back. So this is something this was the manual work at that point, to just like use, okay, this is kind of automatable in the sense that you kind of export all the methods here, and then just kind of like ask it to just pack it up and then send it the same way. But there's also a problem of like how, I guess for people who are familiar, there's by reference and by value, like in terms of how you pass variables on. And so this thing here uses by reference, which means that you send like a pointer to the variable that you want to change into the ActiveX COM object, and then that sends back with the variable change, like in that memory position. But like that doesn't work for Python, which is a much higher level like programming language. So this doesn't work with that. And then so that kind of the heavy lifting was done here to just say, you know what, let's just pack it up, like read the value from like the memory location before sending it back. So there's like a bit of a compatibility layer like at that stage as well. So.
Okay, I think we have the last question.
Yes.
So do you connect to electronic lab notebooks?
Not in this case, but it is doable.
So why don't you not
Yes, so electronic lab notebooks, okay, it is used in the extent that people use Microsoft OneNote for writing their lab notes. And I think people who work with ELN knows that that's probably not like the best way to get data from like external sources to kind of put in. And so at that point in time, I looked into it, and I just kind of thought it wasn't really worth the effort to like make like a thing to just send data into like a OneNote notebook. Yeah, so it's more of like a situation thing that it didn't happen, but it is theoretically possible to just say every time I do a measurement, it connects to a server that just kind of dumps the data there. And I think in the group where I did my next project in, we actually have like someone with software background who's inside, and he actually made like a database. I can't remember, InfluxDB or something like that actually just logs everything every time a measurement is done. That just has a database that goes into like the electronic notebook. So it's more of like situation.
All right, we've approached the end of the session. Thank you very much for...
Thank you everyone for having me and paying attention.